called beats. In fact, that is what I had actually demonstrated to you earlier. What is beats? Beats. Well, the figure shows two sound waves advancing in the same direction. What is the characteristics of these two sound waves? These two sound waves, one has a frequency of 10 Hertz, the other has a frequency of 12 Hertz. That means they are very nearly equal frequency, but not exactly the same. That means they have slightly different wavelength. Now, if you notice, they are starting out in phase, but as they advance, they go completely out of phase. Can you see here? Red wave and blue wave, they are completely out of phase. Compression of one falls on the rarefaction of the other. But as they advance, they soon come in phase. Here the compression falls on compression and rarefaction falls on rarefaction. They are in phase. And very soon they get out of phase. Here they are completely out of phase. And now they are in phase again. Why does this happen? Because they have slightly different wavelength. So, when two sound waves of very nearly equal frequency are sounded together, what will happen? As they advance, they get in phase, out of phase, in phase, out of phase, in phase, continuously. And what do you hear as a result of that? When they are in phase, you hear a loud sound. When they are out of phase, you hear no sound. Again, you will hear this intermittent loud sound, no sound, loud sound, no sound. And this is what we call beats. They have the same amplitude, but they differ slightly in frequency, and therefore they differ slightly in wavelength. If they start out together from a point, they will be in phase when they start out, and therefore you get a very loud sound. But soon as they advance, they gradually get out of phase. You see, if this is where they are in phase, you can see this is where they are in phase, you get a loud sound. But soon they get out of phase. They cancel each other, producing no sound. At some point, they will be completely out of phase. And there you have no sound at all. And again, as they advance, they get in phase. That means you got a bigger amplitude, therefore you have a loud sound. Isn't that interesting? Now, do you think you can produce that effect in actual practice? Well, this is the animation I showed you earlier. The wave above and the wave below. There are two waves advancing in the same direction, and they differ slightly in wavelength. That means as they advance, just watch just one part of it. As they advance, they get in phase, look at that. Out of phase, in phase, loud sound, no sound, now loud sound, no sound, and so on. This beautiful process is what we call beats. So this phenomenon is what we call beats. And you hear the waxing and waning of sound. Loud sound, no sound, loud sound, no sound. So this waxing and waning of the sound as two sound waves advance in the same direction is actually called beats. Now, what is the prerequisite for producing beats? the frequency difference should not be too much. The frequency difference must be very small. If the difference between the frequency is very large, there will be too many beats which will sound continuous. Now, let's see if I can demonstrate that for you. Now here, I'm going to, now this is one tuning fork. I'm going to vibrate this one. I'm going to see if you can actually see this. Alright, let me see if I can show that to you. Now here I have two tuning forks. One is this. I'm going to keep it on a bass here. And the other is this. I'm going to sound each and listen to the sound. That's the first one. That second one. They are very nearly equal frequency. Alright, I'm going to now sound them together. You've got to listen carefully how they sound. Alright, the first one. Do you really hear that waxing and waning of the loud sound, the no sound? Try it one more time. Alright, let me change the frequency slightly and see if it makes any difference. Now, is the beat frequency great? What's the meaning of beat frequency? Beat frequency is the number of highs and lows you hear. And that is actually equal to the difference between the frequencies. Now, look at, listen to this. Can you hear the beats? Alright, I'm going to change the frequency. You tell me, is the beat frequency greater or smaller? There are more beats now. Alright, listen to this one more time. Well, the beat frequency is decreased. That means the frequencies are coming closer together. Now, just one more time and see if you can pick it up. Just one more. Do you hear that? Well, I want to do it one more time. There you are. The frequencies are coming very close to each other. Beats is a beautiful phenomenon in interference of sound. Is that right? Okay. Now let's have a look at a computer animation of beats. I have a 437 Hertz and 437 Hertz. If I sound them together, will there be beats? Let's sound them together and see what sounds like. 437, 437. There are no beats. Let's have 437 and 438. Now, beat frequency here, the difference between the frequency is 1 Hertz. That means there will be 1 beat per second. The beat frequency is the difference between the frequency. Let's look at the difference. Now, another difference, 437 and 442. There is the difference of 5 Hertz. And listen to that. That is 5 beats per second. You can actually play with it. For 43, there will be 6 beats per second. Alright, so we have actually experienced Let's now look at a couple of problems. Two tuning forks have frequencies of 256 and 260 Hz. If the forks are vibrating at the same time, what is the beat frequency? Well, I don't think you need my help to do that problem. The beat frequency will be the difference between the two frequencies. So the beat frequency here is 4. Alright, let's look at another problem. When a violin string is played without fingering, simultaneously with a tuning fork of frequency 480 Hz, beats are heard at the rate of 4 per second. 4 beats are heard per second. It means the frequency of the violin string is either 4 greater than 480 or 4 less. The beat frequency only tell you that there is a difference of 4 Hz between the frequencies. When the tension in the string is increased slightly, you know how to increase the tension on a string? By tightening it. You know, this is how you tune the violin or guitar wire. You can use a tuning fork and listen to the beats and change the tension until the beats disappears. Then the two frequencies will be exactly the same. So when the tension in the string is increased, means the frequency is increased. The beat frequency decreases. That means the frequencies come closer to each other. What was the initial frequency of the violin string? Alright, the beat frequency is 4, means that the difference between the frequency of the tuning fork and the frequency of the violin string is 4. So that tells me that the frequency of the violin string is either 4 less than 480, that is 476, or 484. Now we got to decide which is the actual frequency of the violin string before tuning. Now what happened? When the tension in the string is increased, means the frequency of the violin string is increased, the beat frequency decreases. So can you tell me which of these is therefore the actual frequency of the string before tuning? Well, this is the frequency of the tuning fork, 480. That means the frequency of the violin string can be either 476 or 484. And now what happened? When the tension on the string is increased, the frequency of the string also increases. And what happened? When the frequency of the string is increased, the beat frequency decreases. Now, if the frequency of the string were 484 to begin with, if you increase the frequency, that means it is going to go to 485, 486 and so on, which means the beat frequency must increase. Is that right? But the beat frequency decreased, which means the frequency of the violin string is now approaching the frequency of the tuning fork. That means this must be the original value and not this one. This is how you argue out to solve the problem. So the frequency of the violin string is approaching 480. Therefore, the higher of the frequency belongs to the tuning fork. If the violin has to approach the frequency of the tuning fork when its frequency is increased, that means the higher frequency must be that of the tuning fork and the lower frequency must be that of the violin string. So what's the answer? The answer is 476 Hz. Well, this has been a very useful and interesting lesson, and there is another part of this lesson, 1.5a, that is called resonance. Another very interesting aspect of sound waves, and that I will do later for you. Alright? In the meantime, look through this and see whether you need